All right, so we are running the recording. So, so well, let's have. So we shall start from WASP. Oh, sorry, my wife is calling. Just give me a second. Да. Я уже ел его, да, я попробую доесть его, да, Таня. Сейчас у меня как бы лекция. Да. Ага, чао. Нет, ну давай. Она уже ушла. Может, я ей дам, когда она придет со школы? Если она хочет. Ладно, ладно, ну все тогда, все, пока. Okay, so this is a typical, let me just open this file.
So what file are you opening? Because I want to open exactly the same thing.
Yes, okay, so I'm opening a file which is called concar.bulkc.
Okay, give me 1 second to find it.
Uh,
So it's in software, then Thatcher.
what is it doing? Okay, it opened. Right, so that's the file. Can you see it all? Anything here?
Yes. Well, yes, I can see the Conquer. Yeah.
So this is the old WASP format. It's a WASP 4 format. We will change it to WASP 5 format.
Okay.
In a second, but you see there's this title line where you can put anything you like. This is scale factor, which would rescale the whole system, yeah, which is quite convenient in some cases. Now you have three largest vectors: number 1, number 2, and number 3.
Okay.
These are in angstroms. So
Yes.
And you can recognize here the FCC crystal lattice. If you remember, FCC crystal lattice has a structure A over 2, 0, 1, 1, 1, 0, 1, 1, 1, 0. This is precisely what we have. So this 2.7204 is the A over 2, where A is the largest constant.
Okay.
Yeah. So the largest constant is 2 times larger than this value. It should be around 5.4. Oh, they're taking Windows away. They delivered Windows. We waited for Windows like a month. They delivered this Windows. It's all wrong. Just incredible. Just incredible. Anyway, so when we will do the crystalline lattice, yeah, the crystalline unit cell, if you remember, you expand the primitive cell with a certain matrix T, 3 by 3 matrix, such that all three vectors will be of the same length and perpendicular to each other. So we'll build a cube. In that cube, the sides of the cube would be filled with a single atom in the center.
Yes.
There will be no atom inside the cube. So that's the FCC lattice. So you have on each face of the cube, you have 5 atoms, 4 in the corners, at the corners, and 1 in the center. Right? Okay. So this would require us to expand the cell. But at the moment, this is the primitive cell. And you have 2 atoms in that primitive cell. So you see, you have the atom at the center of the coordinate system, an atom with fractional coordinates 1/4, 1/4, 1/4. Fractional coordinates means that I should take this first coefficient, multiply by the first lattice vector, plus that before. Let me just remind you that because I can hear some sounds coming from some of you, which cause me to believe that something is wrong in understanding of what I was saying before. So I will show this again. Yeah. So these are positions of an atom in the primitives in any cell, in fact, if A1, A2, A3 are lattice vectors of that cell. And therefore, these coefficients must be fractional. They cannot be integers.
Yes.
So in our case, and this is the FCC lattice, as I just said. So you have this is a crystallographic unit cell we show, as I said. This would contain an atom on each face of the cubic in the center and the corner atoms, of course. But this is one private lattice. In the case of the silicon, which has this diamond structure, we have two such lattices immersed into each other with respect to each in a parallel fashion. And therefore, you see, you can recognize here, so this atom, that atom, that atom, that atom, and that atom, and that atom are in the center of each phase. But there's also other atoms which are shifted by a quarter along the big long diagonal. So this one.
Mm-hmm. Yeah.
And this the second lattice. So and we by doing that shift with this quarter along the diagonal, we precisely do this. Yes. So
Okay.
the second atom will be a quarter along the diagonal, big diagonal. And of course, there will be two of them, right? There will be.
Mm-hmm.
Here it is not shown, or maybe not. No, maybe there will be one. No, it should be two. Is that picture correct?
Is it two?
I'm just thinking. Maybe no, it should. It probably should be two. We will see. We will see in a second. Okay. So this is a bulk C in old VASP format, and I can actually read this for as well. So if I so this is let me open a preview and move it to the next screen. So here we won't have anything cluttering the screen. Let me start from the very beginning. So I close camera. So I open camera.
Mm-hmm.
I open in camera now. Now I go to tools and utilities. And then you have two options, left 00 and tether. I click on tether. Tether opens its own window, yeah.
Yes.
Yeah. And it asks me which directory I should use, the previous one or the new one. If I choose a new one, it will open me, at least this is how it works on Mac.
Yeah.
It opens the desktop up, and I go to no OneDrive. I go to software, tools, and tether. This is directly where
for
I would
us
like to
is
work. Yeah. In fact,
for us, sorry. Just for Lev and Connor, for us is just your user software tether 6.04, and then that's it.
Yeah, but you can open any directory. So tether will work from any directory if it is installed properly. And by that I mean, I don't know if you've done this. So there is an environmental variable for tether. Yeah, so this should be set properly. And if that environmental variable, so that variable is called, at least on Unix system, is called, what the hell is called?
Tether.
Home tether, yes. Oh,
No, I did that.
Yeah, and he did that, and he did it for me. So,
sorry, again, go.
No, I've just Felipe helped me go through the install, so I've got home temperature too. Hello.
Yeah. Say again.
Oh, it's just I've got that same install, so I've got home tetra.
You have no tetra.
No,
home
he
tetra.
does.
He does. Yes.
Yeah,
okay.
does.
Sorry. Yeah. Just so do you have this variable displayed correctly?
Yes.
Yes. So if you go to any directory and write tetra, enter, you should be able to invoke tetra. Should start its menu. If that works, that's fine. And Chimera, I think when you click on tether, no, it should find it as well. Right, so we are in here. now. Yes. And so now we open the file with the option VASP, not VASP version 5.2. So this will be 3. So I click here at the bottom, type 3, enter, and it shows me on all contcar and probably postcar files. As well. So we are invoking this one.
Mm-hmm.
So I cut and paste. And when I enter, it's an old format, so it doesn't know anything about the species names.
Okay.
Me about the species name, so I type silicon. There's just one species but two atoms.
Yes.
So I will choose here, instead of sticks, ball and stick. There's some other options, wire and sphere. But ball and stick is probably the best option here. And I go straight to the M menu. M menu, it's a main menu here, which allows manipulation with atoms in the unit cell. So you can basically construct different cells starting from a reference, from a cell which is currently in tether, which we have just read in. So you can construct extensions of that cell. You can add atoms, remove atoms. You can build surfaces. You can add some atoms to be frozen. That is required, for instance, as we discussed, when you do surfaces. You need to freeze atoms in the bottom layers. There could also be some other necessities to freeze atoms, so you can do this here. So all these kind of constructions all are in here. So no surprises. We have just two atoms because silicon lattice contains two atoms in the primitive cell. Here at the top, you can see lattice vectors we have just used, which are the same as in the file, species, and the box. The box currently shows 0, 0, 0, 0. That means we're showing the primitive cell without any extension.
Okay.
Now we can extend the lattice just to see how it looks like. There are two ways of doing that. One way is to properly extend it. It's here, operations with cells. So if you extend a cell, that means that you will really extend the cell. So instead of having a cell containing two atoms, you would have a cell containing more than two atoms. So you will change everything. You will change the lattice vectors, and you will change the content of that extended cell. So this is a proper change. But if you would like to see what is that primitive cell is doing, so in other words, how does it repeats itself in a crystal without actually changing the cell you're working with. There's visualization settings here, which are used entirely for visualization. Yes, so you type VB, breeding box, and then you type how would you like to breed each lattice vector. You can use negative numbers as well. For instance, if I type -1, 1 for the first vector, -1, 1 for the second vector, -1, 1 for the third, I will have my lattice extended. Okay. But this is a virtual extension, so it doesn't change the actual cell. If you look here, the lattice vectors are still the same as before. Also, there is a useful option CO, show atomic positions. CO comes from coordinates. If I type CO, it will show me here. Let me have a slightly bigger screen here. It will show me here fractional and Cartesian coordinates of the atoms of my actual unit cell, which I'm working with. So this is not that. This is 27 times larger.
Yes.
Yeah, because I increased basically each lattice vector threefold.
Lev, can I ask you a question?
Yes.
All right. So when you like on practice, what you're doing here, you only changing the geom file, right?
Geom file is the file which is used for the communication with camera.
Okay, so that's what's changing right now.
File is the only purpose. So what Tether does, Tether, when I do any change, Tether writes geom file on the disk, and Chimera checks that geom file every time it displays something.
Okay.
This is how we make this communication from Tether to Chimera. There's also communication in the reverse direction, and that is done differently.
Okay.
And that was actually a big pain because Tether is a simple Fortran code. It does not know. It cannot do this kind of things like reading something. No, it is possible to do, I suppose, but it's difficult. Anyway, so there is a way to communicate between the two, and this is done via this interface. So because Tether, as I said, is a Fortran code which is precompiled, and therefore it has nothing to do with Chimera at all. Chimera invokes Tether inside that window, and it has this input panel here as well, input bar, and it is possible to transfer information into that input bar, and then Tether can understand that information. So this is the way it is done.
Okay.
So that input bar somewhat replaces for Tether the command line of the screen. And this is useful because you can actually mark atoms on the screen and let Tether know what are the atoms you marked. For example, if you want to freeze some of the atoms, or you would like to move an atom. So I will show you that. And that is very, very useful. So there's a two-way communication. Okay, so as you can see, I'm still working with my primitive unit cell, but for the presentation purposes, visualization purposes, I can see what my lattice is, and it looks like silicon.
Okay. Yeah.
You know, it's a hexagonal kind of thing, a tetragonal structure. Each atom is connected with 4 neighbors, so this atom is connected with 1. So this atom, I can actually mark this atom. So it is marked. On my computer, it is control. Sorry, Tim. There's anywhere I can go.
No, it's fine. No, no, just get your top.
Ah, nice. But you're not going to play your stupid game.
It's a good game. I'm just jealous.
I'm just jealous. Yes, maybe you're right. So I can mark all these atoms. So I do it. Oh, unfortunately, I can mark only one atom at a time unless I run it with the mouse like this. Yeah.
So you just click and you can mark the atom?
Yes. No. You have to press Control on my computer. You have to press Control and then click with the mouse.
Okay.
But on your computers, it could be somewhat different. I don't know.
In my computer, you can also control and then drag, and then you select a bunch of atoms.
Also press Control and try to drag the mouse and make a box. It would mark all the atoms within the box. Like if you press Control at the empty space and click on the empty space, it will remove all the selections. Yes. So what I want to say that this atom, if you take this one, it is connected with 4 atoms. This one, this. So let me mark this one, this one, this one, this one here, and at the bottom this one here. So each atom is 4 coordinated, and it appears to be in the center of the tetrahedron made by these 4 atoms it is connected with. Yes.
Yes.
All right. So so it looks like my lattice vectors are good, and I can save, by the way, that file. Let's save it. So I press S. You see, there's a save the input file option, and now it gives me a choice of saving this input file in different formats. And this time I will use VAS 5.2 format. So I press 8. And I press, now I have to type the name of the file. Let's call it postcar, why not? Postcar bulk silicon 5.2. bumps, enter. Now it asks whether I would like to save it in Cartesian or fractional coordinates. So what that means, previously we had this keyword direct here. Means that these positions of atoms will be in fractional coordinates. Yeah? Fractional coordinates are not very useful sometimes when you want to see where atoms are actually, because you have to multiply tetra. Of course, if you read this atom in, go to the M menu and use the option CO, you will see all the Cartesian coordinates. But sometimes it's useful to see them in that file, because this file is a text file, so you can see, you can open it and see the content without any software, just by using very simple editing tools or viewing tools. So in that case, the keyword should be Cartesian, and here you will see at the bottom actual Cartesian coordinates. So let's choose Cartesian. It could be a small letter or the capital letter, doesn't matter. So I click here to make enabled that window, because I used another window before. So I click here and press C. Now the file saved, and if I go to my directory, I will see that there was a file created, this one, yeah. Oops. So I can have a look at this file, Oscar. Here we go. That's the file, and you can see it's a new WAP format. First of all, I have silicon appearing, silicon line appearing, so it knows what the species, what is the species. I have selective dynamics, and I have Cartesian keyword, and these are now Cartesian coordinates. Also, look at this letters here at the end, FFF. FFF means frozen. So X, Y, and Z coordinates of that atom, of each of those two atoms, are frozen. Yeah? So they will not participate in any relaxation. So this is my cell now. So now I can create, so once you have this cell, what you can do, you can run VAS with a certain k-point sampling. And by the way, k-point sampling can also be saved. Let me show you this. But it's you don't need that, use Theta for that, but it's also possible. If I queue, with a queue, I go exit that menu, and there is a k-point generation here. So I go to k-point generation, kp, and here I have to specify whether I'm dealing with the bulk or with the surface. So you see this 0 here. Now it is the bulk, but if I type 0, it goes into the slab calculation. If I type 0 again, it goes back to bulk. So you have bulk. It shows me reciprocal lattice vector straight away. And now you have 3 options: density of states, band calculation. Each of these options would require a different k-point sampling, but let's consider just 3 self-consistent ordinary calculations, in which it will create Mann-Hossbach sampling of the k-points. This is silicon, so probably 4 by 4 by 4 would be a sufficient number of k-points for that system. 32, I say yes, I'm happy with that. Oh, no, choose another parameter, I just press enter. So all done, Q. And if you now look at our directory again, we see that it must have created, oh no, not yet. Oh, that's interesting. Oh, maybe I should say save.
So I think.
Oh, what's happened? Oh, wait, give me a second. Let me click on all output. Then I have access to all output of Theta during the whole session. That's useful to see
if something went wrong.
You see what I've done? I clicked Q to return to the main menu instead of clicking save. So k-points file has not appeared. Yeah. So I have to do it again, I suppose. So I go kp 3 self-consistent, then 4 by 4 by 4, and now we have to say okay, enter. Now we have to say save. Unfortunately, the way the Theta was built, it was not built from scratch. It was built on top of another Theta, which I worked with a very long time ago, when I realized I need to make it proper. but I was probably a bit lazy, or not lazy. But you have a pre-existing structure, and sometimes it's difficult to break the structure, and you have to write the code from scratch, and probably I didn't have time for that. So when I say save, it still, even though I have chosen already the format, it asks for that format again. So I choose 8. I choose the name of the file. Let's choose the same name as we had before, postcard. Even though it has nothing to do with the key point sampling that information. Yes, but it still requires that Cartesian. Now it's done. We go Q, go to the main menu, and now key points file should be here. Yes, we have key points file. We can have a look at it. That's the key point file, which contains all the key points. Yeah, 32 of them. But you see the number of key points here is smaller because of symmetry. Actually, I don't remember. Is this correct? Probably.
It creates 32. No, that's fine. It creates 32 points.
It does create 32 points.
Yeah, it does. Well, I'm counting here on mine. I did exactly what you did.
Yeah. So this command WC in Linux shows me the number of lines. And you see the number of lines is 35. And we have
Minus
3 extra, so 32.
Yeah. 32, yeah.
Because this looks odd. If you look at this, it doesn't seem to be 30. But apparently there is 1, 2, 3, 4, 5. Yeah, apparently there is. Yeah. Interesting. So it creates all 32 points. Yes.
Okay, so these are the 32 points inside the 4x4x4
No,
grid.
these 32 points inside the Boolean zone.
Oh, okay.
Yeah. This is the reciprocal lattice.
Yeah, okay, yes.
In fact, so these are all shown using fractional coordinates. So these are all fractional coordinates. So these are coefficients to the reciprocal lattice vectors. And these are weights. Weights are needed because of symmetry.
Okay.
The sum of all weights should be 1.
1, okay.
Yeah. So we have just created a bulk silicon structure.
Yes. Okay.
Now let's try and the key point file which we need. Of course, in-car file has nothing to do with Tether. In-car file you create yourself. Yeah. But for a change, we can also let's save that file. So I can do it from the main menu. Go save in the CP2K format. CP2K format is quick step input 2. Yeah. So let's call it bulk C, and we type extension as well.
What's the extension? ENP.
Yeah, ENP. But I think this is just for Tether. I think I can't remember. CP2K doesn't mind any name.
Oh, okay. I don't know.
So we're done. Press enter. You see, it wants you that you have to edit that file because that file would not contain all the information required by CP2K. CP2K input file is like a collection of all input files of VAS.
Okay. It's not just the position.
All the logical information. So let's look at this file. So this is the file it creates. It has all the important information. You have to put the basis set, pseudo potential information here in this box is missing, but your cell information and coordinates of atoms are here. And you also have, because in our input file, if you remember, we have this FFF at the end of the file, so all atoms are fixed. Also, it put the nested structure necessary for freezing these two atoms. So it has this correct. So fixed atoms, components X, Y, and Z, and list
1
to 2.
Okay.
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 Yeah. So we have created this file, and in fact we can read this file again. I actually may complain, but let's just try. From the main menu, I go to read. Now I go to quick step, which is 2. And we take this file. Can you see this? Yes, here we go. Of course, you don't need to cut and paste. You can just type. Yeah, it did it. Yeah, so it's happy. So it ignores all the places in the file which have nothing to do with geometry, and so Theta itself is happy. Okay, so we have all the information. We can just go to the M menu again and see go CO just to see that atomic positions are fine. Yeah, that all seems to be fine. Let me close this. So atomic positions are fine. Atoms are still frozen. All right. These two columns. The tag column shows if atoms are tagged. For example, you would like to freeze a particular atom or atoms, or you would like to move a particular atom, in which case you will see if you type CO, a tag on that atom will be chosen, selected.
Okay.
Part is used, if I remember correctly, when you say combine different systems. For example, you created a surface and you put a molecule on the surface, so the molecule can be read in from another file. They will be automatically treated as two parts. But to be honest, I can't remember that exactly what it does, but it has to function sometime. Yeah. So this I kind of. All right. Okay. So type enter. We're returning to the M menu, and now let's create a proper cell extension. So we would like to create a crystallographic unit cell. Yeah. So this is FCC structure, we know that. But let's create a crystallographic unit cell. So for that, we need a proper extension. We can create breeding extension. Let's do breeding extension. What is breeding? EX, this option here.
Okay.
Diagonal breeding. And that works exactly the same way as BB option. So you type, say, 0, 1, for instance, 0, 1, 0, 1, and 0, 1. That would mean 2 by 2 by 2 extension. But you see, it made this extension, but you have too many atoms. This is because BB option is still minus 1, 1, minus 1, 1, minus 1, 1. You see? So in order to remove that, I would just type B0. B0 would nullify the breeding box. And you see, now I have precisely as many atoms as I need to have to have, which is, if we go to CO, this would be 16 because we have 8 times cell extension and 2 atoms in the primitive cell, so 16 altogether. So this is now my new unit cell. By the way, you can show atom numbers here if you click. You can show species if you click. And you can rolling my mouse, I can see this. Unfortunately, they do not much increase these notations, these labels. They still small, which has nothing to do with Theta. It's of course Chimera. Maybe Chimera can do this, but we haven't figured out how to do it. Anyway, so if I remove this, they disappear. The other thing which is useful in our box is the axis, toggle axis. So now we have axis shown, and you can see that axes are marked Z, Y, and X. So this would probably be my coordinate system, X, Y, Z, like this, yeah? Using my option key and mouse, I can move vertically. Otherwise, without pressing any keys, Chimera just rotates the system. And if I use Control, I mark objects, or it still rotates, yeah? So if I, oh, come on. Oh, wow. Okay. So if I press Control and move the mouse, it will rotate. Okay. So you need to play with this a little bit. X, Y, and Z. You see? You can change the size of the axis here. For example, let me put 10. Update.
Okay, just
no. There's something wrong, I suppose.
or just change the
sorry.
right?
This changes the zero at which the axes are shown. But if I want to resize them, I can't resize them individually. Now they are 5. I can make them 10. Now it's simply bigger. As you get as bigger and bigger cells, you would like your axis to be longer, so you would be able to see where things are. You can also show. So let's remove this axis now. And you can also show your lattice vectors. So my lattice vectors are shown here in the current lattice vectors box. And by the way, we made an extension so that remembers the previous set, and it's shown as the reference lattice vectors. So reference lattice vectors, you can see this. Oh, by the way, I think I wanted to show you something and I forgot. Now it probably will not work, but let's see, maybe it will. So this is my primitive cell. This is down now 2 by 2 by 2 extension. You see, the lattice is still FCC because the lattice vectors still follow this format 0, 1, 1, 1, 0, 1, 1, 1, 0, yeah? So we haven't constructed a crystallographic unit cell. So our extension, this diagonal extension, when each lattice vector it was just by twofold extended, will not make trick. Yeah. So let's try undo option if we can return back to this. So I type undo. Undo is somewhere here. Here, undo the last step. Yep. So we return back. Now we have both lattices the same. You see here. And now we can make a proper extension. Proper extension will not work with the diagonal breeding box because this time we need to specify. Tim, no? Where? I need the power. If you can help me to get the power. No, I mean there. It's so Nika can hear me. No, here from here.
Well, just throw them upstairs.
Sorry. Okay.
This also means that if she needs to pick up the baby, I can come straight in.
Oh yeah. Okay. So where's the power nearby? It's behind. Thank you. Good. Where's my mouse? I have my mouse. Yeah, it's all working. All right, so okay, so where are we? So we return back. So we need to use general breeding, SU, super general breeding. So we go SU, and now we specify the matrix elements, 3 by 3 matrix, 9 numbers, integer numbers, which would make the transformations. I derived for you that matrix before. It has elements -1, 1, 1, 1, -1, 1, and 1, 1, -1. As you can see, we constructed now something. But what happened to the lattice vectors? Look at here. They are perpendicular to each other and of the same length. We have just constructed a crystallographic unit cell. Number of atoms, total number of atoms now is 8.
Yes.
And this is what we should have. because the unit cell, if you remember, increased 4 times. We had 2 atoms, now we have. So we have just constructed crystallographic unit cell. Now we can try to build, to show these lattice vectors. Actually, there's a way to do this. Maybe I should make it like one option. At the moment, it is not like that. But VS show vectors. So let me choose VS. And how many vectors I show? I would like to show 3 vectors. And now it asks me which vectors I would like to show. Of course, I can type, but I'll just cut and paste this information, which is here. Vector 1, vector 2, and vector 3. As I said, I should be able to do it with a single option, and maybe I need to change that for that. Oh no, we didn't do this. And now I can see my 3 actual lattice vectors. These are my lattice vectors. So now you should be able to see why this is called FCC. You see, that atom is exactly middle of that face.
Yes.
Yes. And and the same is true for this atom. This atom is also in the middle of that face, and that atom in the middle of the XY face. Yes. By the way, toggle axis as well. So these are my Cartesian axes, and you see my lattice vectors are along those. Yeah. But there's also this atom here, which is shifted along the main diagonal by quarter of it. This is the second silicon atom. All right? And actually, if you approach your mouse, it shows number 5.
Yes.
So if we go to CO, that atom is supposed to be number 5. And indeed, if you go to number 5, you see it has fractional coordinates, quarter, quarter, quarter. It is that atom. It is along the diagonal, and you can easily calculate the diagonal. So you need to take 5.44 multiplied by square root of 3. So let me do the calculation. 5.4408 times square root of 3, which gives me 9.42, and then I divide it by 4, 2.35.
Okay. So that's the distance between 1 and 5.
Oh, yes. Yes. So this would be that distance.
Yes.
But the same distance I can obtain if I take this number 13602 and multiply by square root of 3. So I can divide that number I just obtained by square root of 3, and I have 1.3602, precisely this. Okay. Guys, everybody,
So cool.
do you follow what I'm just saying?
Yes.
Everybody, we're all on the same page?
Well, I am.
You are,
Yes.
but I'm asking the others.
Yeah, it's all good.
So good, good. Okay. All right. So I'm just taking you around different options in that. So we have just constructed a crystallographic unit cell. We can now BB this crystallographic unit cell. Let's BB it, say, along X, Y, and Z just twice. Yes. So I will type 0, 1, 0, 0, 1. Just remember, this is not, we're not changing the cell. We're just changing what we show on the screen, yeah?
Yep.
And now you can see, let me make it smaller, you can see my lattice. And now we should be able to see all the primitives, all the crystallographic cells. So these 4 atoms, they form that face. these 4 atoms form that face, but you have all sort of other things here there, yeah? So we have just constructed the lattice. And by the way, yeah, we don't have the second atom on the same diagonal I was thinking before. So we have it on the other diagonal. So it's all right there. So everything is correct. So this, we built a very nice cell. And in fact, if I choose, say, that cell as my cell, and I will breed it along the x and y direction, and then I will increase the lattice vector in that z direction, I will create 0, 0, no, would it? Yeah, 0, 0, 1 surface.
Yes.
Yeah. Okay. So, but this was just visualization. Let's remove visualization with B0. We return back to our crystallographic unit cell. When you build something, you can build it starting from the crystallographic cell or from the primitive one. If you start building it from the primitive one, you have a little bit more flexibility because your building block is smaller. Here, the building block is larger, 4 times larger. So when you start breeding this one, it would breed the whole thing. Yes. So if you breed it, create a surface, your surface would contain more atoms, which you may actually need. So let's see if I can do undo here, because I don't think I did anything else. Yes, I returned back to my primitive cell. You can undo only the last construction step, only the last.
Okay.
This tether is not as sophisticated as any commercial software, which you can come back to as many steps as you like. Here's only one step, and in fact, it would be nice to have that option of going back as many steps as you like. But this is what I have. All right, let's now construct. So we can remove vectors.
So I think you click toggle.
These old vectors, right? If I type, what will happen if I say 0? I can't remember now. It still displays them.
For me, I just click on toggle. Yeah.
Toggle vectors, yes. Okay, so now we have our primitive cell, and let's make a surface now. We would like to build a 001 surface, a very famous surface of silicon. So we should go to the option which is called build surface, SR. This option is here. In that option, first of all, we need to create a crystallographic unit cell. Tether doesn't know all these matrices, so you will have to really investigate yourself what is the matrix which is to be used to construct a crystallographic unit cell. And this is because Miller indices, which we need to use in this case, they refer to crystallographic unit cell rather than the primitive unit cell. Of course, you can construct Miller indices for the primitive cell with a reference to the primitive cell, but then they will be different. Remember what Miller indices are. Miller indices, is it here? Probably not here. It's the next file. Yeah, Miller indices. Hopefully it's here somewhere. No? Oh, it will be the reciprocal. Sorry, so I'm just trying to find the right place. So crystal planes. Oh, by the way, I can send you all these files. That would be useful for you, probably. Yeah.
That would be very useful.
Yeah, very useful.
Please remind me. Please remind me, and I'll send them to you. Yeah.
I will.
So direction of the plane is specified by 3 Miller indices, which are 3 integers, and they show a fraction with which that plane would cut the Cartesian axis. Oh, not Cartesian vectors A1 and 2 and 3. So you can read this, but the point is that 001 surface would be like this. Yeah, 111 would be something like that. And these Miller indices, they correspond, which is important, to the factors in the linear combination of the reciprocal lattice vectors. So if I want to construct a plane which I call 001, that means that these two terms will be 0 because it will be 0, 0, and this will be 1. So a vector B3 of the reciprocal lattice associated with the crystallographic cell will be perpendicular to my plane. In the crystallographic cell, in our case, is a simple cubic lattice. So the lattice vectors are along x, y, and z. And therefore, reciprocal cell would also be a simple cubic lattice. And therefore, vector B3 will be along the z direction. So my G would be basically a vector along the z direction. So my plane will be perpendicular to that direction. So this is that plane, right?
Mm-hmm.
And this is what we want. Okay, so we have to type SU and do what we did before with these numbers, remember? And now we constructed a crystallographic cell. So it shows you these crystallographic cells, vectors as before, remember? It shows you also our primitive cell direction. And now we are ready to type Miller indices. So this is MI 001. It even shows some information here. Okay, so we have done Miller indices. It shows the direction of the normal, as expected in this case, is the z along the z-axis.
Mm-hmm.
Yeah. Now the next option is this: choose lattice vectors 1 and 2 within the plane. Remember we discussed that. Yeah. Now what theta does, it finds a linear combination of vectors such that the first one and the second one would be within the plane of our choice. However, we'll still be within the primitive unit cell construct. Yeah. So
Okay.
I do CP. It created my new lattice vectors.
Mm-hmm.
But this is still the bulk. So you see the first vector and the second vector are within the xy plane. And my construction is rotated in such a way that my plane becomes x and y plane, which is also very convenient. Yeah, because you will also always have z-axis perpendicular to your plane.
Okay,
and
so
yes,
sorry.
go.
By default, it chooses X and Y.
Yes.
Okay, good, brilliant.
Yeah. So
Okay.
I don't think by default it would be the right word, because by default assumes that you have another option. And this is just an automatic option. I don't think there is another option. It's just
Okay,
an option implemented, right?
Okay, okay.
Yeah.
But it's the logical one.
There's a logical one, yes.
Yes.
I
Okay.
can't remember now. Maybe if you don't do this CP and just go to Q, maybe it will keep it as oriented as it would.
As it is.
But I don't know. So now we
Okay.
type Q. You can undo, but we type Q and go to the M menu, and now you should be able to see the following. The first lattice vector is this one. The second lattice vector is this one, both within the xy plane. The third vector is this one. Now it is out of xy plane, and that should be the case because the third vector cannot be coplanar with the first two, coplanar with the first two.
Correct.
Right. So it sticks out, but we're still within our unit cell. You see, the number of atoms is still 2. This is my reference lattice. This is my new lattice. And if you look at the CO, it would still contain 2 atoms. So we're basically still within the realm of the primitive cell.
Yep.
Now we can construct a whole slab. And for that, we need to breed the system along the third lattice vector, because at the moment we have only a single lattice plane created. Yeah, if I breed this, just let's breed it. So I breed, say, minus 2, 2, minus 2, 2, but in the z direction I would not breed, so 0, 0. In which case I'll have just one lattice plane.
Which is your 0, 0, 1 surface.
Yes. Okay, you may argue these are two lattice planes. There is a matter of...
Well, yeah.
There's a matter of definition. So I remove the breeding. So still two atoms as before. And now I will breed it along the third lattice vector. How many planes do we... Let's have 4 planes, okay?
Okay.
I go in the diagonal breeding, EX.
Okay.
I do not breed along the first 2 vectors, so 0, 0, but along the third vector, I breed in that direction, downwards. I would like this atom to remain on the surface. So my breeding would be minus 3, 0, if I remember correctly. We can undo if that is not working. No, this is wrong. So undo. Is it possible to do it? If I do 0, if I do...
Uh-oh.
0, 3, it will go upwards. Oh, no, that's actually correct. 0, 3, it works in the way I want. Yeah. Yeah. So what we have just created, let's BB this again, just to see what happened. And again, I do not BB in the Z direction. So I have a slab. But you see, the lattice vector, the third lattice vector, the first 2 lattice vectors are still the same. The third lattice vector is increased 4-fold. And by the way, the number of atoms here is 200. This corresponds to this extension. In the system, if we go CO, we would have how many atoms? We had 2 atoms in the primitive cell. We extended it 4 times, 8. All right?
Yes.
Okay. Yes. So we have 8 atoms. So I remove BB for the moment. So we have the same 8 atoms. Good. And now, in order to create a primitive surface, so this primitive surface unit cell, the unit cell which contains the minimum possible number associated with 4 layers, I have to choose the third lattice vector, large. You see, if I don't do this, what will happen? Let's do BB again. Let's have minus 2, 2, minus 2, 2, and say 0, 1. You see what happened?
Yeah, you just have...
Where's my mouse? Yes. I would just have my cell 2 times increased. There's no gap.
Yes.
There's no gap. Yeah. It just became longer in that direction. So in order to avoid this, I need to change this lattice vector to something big. So there is an option for that. And the option is change the third translation, which is this one here, C3. So type C3. And now I just type a new translation, 0, 0. Okay, I need to be careful, because if my third translation would not be big enough, my slab may overlap with itself. Yeah, and it could be a problem. So suppose, so here you can see that it's 7, 7 minus 10. So if I type 10, let's see what happens. Will that crash?
Don't you need to give like all 3 vectors?
Oh, yeah, sorry. Okay, so we just type this and then...
It's gonna make a mess, but yeah.
Yes, there will be a crash. Let's say yes, what will happen?
I have no idea.
Error.
Error.
Too small. Stop. Okay, tether nicely crushed. Yes, so we have to restart tether here. Use the previous directory. So let's quickly go through all these steps we had. So we can use 8 because we created. Oh.
Okay, you created the VAS file.
We created the VAS 5.2 version as well. So this will be this file. We go to the M menu. We have a CO primitive unit cell. So we go straight to the surface build. Oh, no, SR. Now we need to make the extension. What happened?
You made a mistake on the first one. You only gave 2.
Oh dear, oh dear, oh dear. Let's do it again. It's obviously wrong. Minus 1, 1, 1, enter. 1, minus 1, 1, enter. 1, 1, minus 1, enter. Okay, that's better. You see the vectors are right. Merely indices 0, 0, 1. Yes. Now CP and Q. So we returned here. Now we extended in the direction EX. So 0, 0, 0, 0, and 0, 3 for so we should have. Oh, now we have because Z is like this.
Yep.
Okay. Now what we want to do, we want to change the lattice vectors. It is not C3 option, it's C1, obviously.
Okay.
Just change one lattice vector. It asks which one, the third. And let's make it 0, 0, 11. Okay, it eats it up. So let's do BB. BB. Let's not make it very big. So minus 1, 1, minus 1, 1, and here we have it 0, 1. You see what happened? My lattice is not big enough. So these two slabs are very close to each other, dangerously close. So this is not what I want. So I will change, let's keep DBB enabled. So I go to C1 again, and let's make it 0, 0, 15. Oh, sorry. Oh, it's again. It asks which vector. Third, 0, 0, 15. Yes. Okay. Now you see, we have a gap. So this time we have constructed a slab. Maybe the gap is not big enough. But our vectors, let's see what our vectors are, lattice vectors this time. So again, we go to VS, display vectors. And now I take this vector first. Are you repeating my steps, actually?
I am. I'm doing exactly what you're doing.
Oh, that's very good.
I cannot do it at the same time, so I just...
Fantastic, fantastic. So you have the same output as me.
Yes.
Toggle. Oh, why it doesn't show these vectors now?
Yeah.
Oh.
I don't know.
Because I'm stupid. I'm not looking at what I'm doing. I say 3. Number vectors.
I did exactly the same error as you did as well.
Yeah, good.
I
Thank
wasn't
you very
looking.
much. We're all in the same boat. This boat of stupidness.
Yes. There you go.
You're probably using a mouse, you're faster. So I have, yes. Let me remove my axis. These are my lattice vectors, you see? My lattice vectors So in the surface cell, the 001 surface, my first two vectors just directed along the surface to two nearest atoms, and my third vector connects two equivalent atoms on both surfaces of these two neighboring slabs.
Mhm.
Yeah, yeah. It connects this atom to this one, which is equivalent atom. So when you would like to have a certain gap, for instance, you would like to put a molecule here, you have to make sure that this vector is long enough, because you have to ensure that there's a sufficient gap between the two slabs so they would not interact. This is not enough. This is definitely not enough. And then on top of that, you put a molecule on this side, yes? And the gap would be even smaller between the molecule and the slab. So you have to take this into account. So for our purposes, if we want to put a molecule, and we will probably put a molecule, we'll try. Let's make this even bigger. So 0025.
25.
Yeah, now it's big enough, probably. Yeah, so it's very long.
Yep.
So, and I believe I would be able to put the molecule. But in fact, the gap, as we discussed at one of the previous sessions, the gap should be checked by a computation, yes? So you run a slab calculation without any relaxation. You just look at the total energy. Only the electronic part should converge. No relaxation. So we call it one-point calculation. So you do write this calculation for several values of this third lattice vector. Yes, and
Yep.
you check when the energy stops changing, and that would be your point. At that point, your lattice vectors, when you put a molecule on top, you probably need to increase the gap still, unless you have from the very beginning the gap big enough.
Okay.
Yeah, don't forget, but when WASP does its calculations, it has a grid. Grid has impact on the memory. Because it keeps all the direct space information on the grid. And if the lattice vector is very large, there will be many grid points, in this case along the z direction. The calculation would become more expensive. This is not the case for CP2K, by the way. And CP2K is using a localized basis set. So if the gap is large, gap is small, it doesn't really matter.
Okay.
It has in one particular, when it calculates the Coulomb interaction, it's using plane waves at the grid, but this doesn't seem to impact a lot on the total calculation time. But in VASP, it's important to remember this. So don't make this vector 100, say, if you don't need.
Okay.
Yeah.
Okay.
Just be careful. Yeah. Always check. All right. So we have constructed the surface with you, yes? But this is the primitive surface. In fact, it is not silicon 001 surface reconstructs. And in order to study this reconstruction, we need to go beyond the 00 or 1 by 1, say, surface structure to 2 by 1 or 2 by 2 or 4 by 2 even.
Okay.
So let me remove BB again. So now we back to our surface. When we do surface calculations, we also need to make sure that the surface structure corresponds to this slab structure corresponds to a surface, which means that we need to do something else here. First of all, silicon is a covalent system, so we have to terminate bonds which we have here. And now I have made a mistake because I need to put a hydrogen atom, but the algorithm is based on lattice vectors which we have now. So we have missed a step. in order to return back to that step we had before, we need to change the third largest vector. But that is not difficult to do because we can change it back to what it was before. Let's just search for that.
It was not 25, 15.
11. Yeah, here we go. That is my largest vector we had before. So let's go to C1, third vector, and we invoke this. Now we are back in our bulk construction. Let's just do BB just to see that we are in the bulk. Just 0, 0, say 0, 1. Yeah, we are in the bulk. You see, it nicely repeats itself. No problem.
Yeah. The vector just doesn't change because we haven't changed it, right?
Which vector?
The
Oh, these ones.
Yeah,
Oh, yes,
yeah, yeah.
but we didn't touch them. If I implement that option that every time it will show the actual lattice vectors, it will update automatically. But for the moment, it just shows 3 vectors which we inputted. Yeah.
Okay, yeah, fine.
Let me just remove them. Or maybe let's keep them. Doesn't matter.
Okay.
So BB I will remove. So we are back into the bulk construction. And now we would like to terminate these atoms with hydrogens. Which atoms we need to terminate? Probably these ones, which are at the bottom, right?
Yes. If you're gonna extend.
Yes.
Yes.
So the way it works is that there must be just one atom. Let's check this out. So I do BB this time along the surface only. And let's have a look so if I take this, is it enough? It's probably not enough. Let's do BB beta 0, 2, 0, 2, 0, 0. Now, let's zoom in. All right. What just has happened is that these bottom atoms would need to have 2 hydrogen atoms to terminate them.
Yes.
Each. Yes. Not just one. There are 2, because they lack 2 bonds. Remember, this should be the center of the tetrahedron.
Yep.
So good. So we have an option for that. Terminate with H atoms. So I type H. Yes, and there is a distance between an atom and H atom. Is set up to 1. So I can change this default HD. Say put 1.1. Just for you to see that you can actually. But that distance needs to be optimized. You should run a VASP calculation with these hydrogen atoms and allow only hydrogen atoms to relax. I'll show you how to do it.
Okay.
So, yeah, now we go to H.
So wait, H is where?
H is here. Other operations, under other operations.
Other operation. Okay.
Yes.
Just making sure that I know where the thing is. Okay. Okay. Yep.
And now it asks me to specify a range of atoms with 2 integers, the ones which I want to terminate with hydrogens. And I really don't know which atoms are these because I did BB. So you see, BB is not a good idea. We should have. So let me just type 1. This is the range. So it terminated with hydrogens. You can see all atoms here at the top.
Okay.
All the unsaturated bonds were terminated, which is a bit weird. White has them.
If you try 8, I think it's the right one.
But what I will do, I'll simply do undo. But I'm confused as to why it shouldn't have done this. Oh, of course. This is because I think it uses this Is it possible? Or it uses this? It uses this reference vectors. So undo will not help. We have to start again. We have to. Oh no. That should be not the case. Oh yes, of course, because it did it for the surface atoms, but it should do it for these ones and this. Okay, so let me do undo BB. So that atom, I'll show numbers.
Yeah, it's number
Atom
8.
number 8, as you said.
Yeah.
Okay, and now I go to H option. Now I specify 8, 8. It is wrong.
Why is it wrong? Because the other side?
I can't remember.
Okay.
No, why is it wrong? Oh dear. Why is it wrong? Let me see what will happen if I type it for 7. Huh.
That's interesting.
Oh.
Do you need to do this before you extend? I don't know.
I forgot this. You see, I haven't done this for such a long time. Let's go to this to the tutorial and quickly have a look what needs to be done actually.
Okay.
Maybe there is an option you need to use. Okay. We've done all this. We constructed the surface. We choose milli indices 0, 0, 1. Next page. So now we arrived at that construction. Yes, that's the same as we have, right?
Mm-hmm.
Yeah, that's the same. Here, just explain these lattice vectors. It is still silicon bulk, okay. The options number, the options titles are really different now. Okay, let's go next page. But the idea of the okay, so you see, it should have done this. To terminate with H atoms, we first need to make the current cell the reference one.
Need to make the current cell.
Oh, I completely forgotten about this. Where's this SR? No, SR is the build surface.
Okay.
So basically, we need to change this. Should appear here as the same thing.
Yes.
Yes, of course. Otherwise, because it starts building. Yes, I know what happened. But I can't see this option. What happened?
If I view the surface.
Adjust to reference file. No, this is different. Yes. SR. There is the option. Set current geometry as reference.
Oh, SR like capital R.
Capital R, yes.
Because there's SR for the surface.
Yes. So let's remove these hydrogens. We remove this, but we can't remove that one. But that hydrogen is actually a proper atom. So we can find its number. It's number 9. Yep. And we can also just let's mark this atom with the control. I mark this atom. Now you see that I can type the option.
You need to tag the atom first.
Yes, so I tag the atom. Now you can do. There are 2 ways of doing that. Okay, you can tag the atom. Let's tag the atom first. Tag the atom. Now here I got get selection here.
Yep.
It gave me this 9, which I typed. So now the atom 9 is tagged, and if I go to CO, you will see it's tagged.
Yes.
Next, once this atom is tagged, I can remove it. This option, remove, RM, remove target atom. So now done. So we were now at square one again, yeah?
Yes.
We turned back completely.
Okay.
Right, now we type SR, capital SR, and in these two reference, we should have exactly the same vectors now. Yeah. Do we have? Yes. Yes. Now let's use the H option. Let's double check so we will not make a mistake. So we done SR. Now we do H for that atom and remove all the unnecessary hydrogens. Okay. So now we type H.
H.
8.
Okay, and then now we remove the atom.
It's better now. Now we have only to remove this hydrogen because it is directed towards that atom. We don't want that. Okay. That hydrogen has a number
11.
Number. Oh yeah, this number is wrong. So this has a number 11. You think?
Yes. If you press show numbers, it's.
If you press, I pressed with the. Where does it show that?
On the right. On display options.
You see, if I press get selection, it's way on the right. In my case, on my screen, it doesn't show that.
Oh, it does. So on the right, on the top part of the screen. So right and top.
Chimera screen or Tether screen?
Tether screen.
On the right? Where?
Yes. So there's ball and stick, right?
Display option.
And then there's show numbers.
There's a display option.
No. Go up with your mouse.
Yes.
More up.
Yeah.
Now right. Right. A little bit down. There you go. Ball and stick. Keep going down. There's show species. Stop. You press it. There's display options left. There's stick, ball and stick, wireframe.
Oh, yes, of course. I know that. I can. Yeah. But what I was thinking that when I use the
okay, I see what you mean.
Then it shows. Yes. Of course, I can do this. Yes, but you see that when I approach an atom, it shows some information. Number 5, U and K, 1, H3. It would be sensible to show because it's bigger, to show the atomic number on my list. It doesn't.
I see. Okay. Yes.
Yeah. Of course, this show numbers. I know. Yeah. Okay. So this is number 11. So we need to remove that number. So we can tag that number, or we can simply type RM, which is another way, and then it asks for the list. Ooh, 11.
Okay. Yeah, you can do that.
Now we have these 2 hydrogens at the bottom, and now we can BB. So -2, and say 0, 1, just to see that we have a gap. Right.
No, we don't.
We don't. We don't
We
have.
don't because
We
yeah, we
don't
don't because
have a gap. We have rubbish. You have these hydrogens at the bottom of which that's very funny. But you can see that these are nicely terminated. Yes, at the
yeah.
bottom. Okay, so we need to change the first lattice vector, the third
Uh-huh.
lattice vector. So C1 0 0 23. Again, I made this mistake. 3 0
Oh,
0
I
20.
did the same mistake again.
Yes, it's annoying. And now we have them separated. Let's make them smaller. Okay. That's nice, isn't it?
Yes, it is.
That's nice. So we have this done. Okay. They're nicely terminated. We have a proper surface, you see?
Uh-huh.
That's what people would show in papers, something like that. But you have these atoms at the top. They're actually not happy because they don't have neighbors, and the number of bonds they have only 2. If you look at each atom, it's only 2 times coordinated.
Which atoms are not happy? Sorry, say that again.
At the top.
Yeah, but yeah. But those are the surface atoms, right?
Give me a second. Give me a second. My daughter asked me something. Maybe she needs help. Maybe we'll make a little break.
Okay. Ah, that's so cool.
It's gonna be fun to play around with.
Yes. Yes, it is. It's so I don't know about you guys, but I think that's so cool.
Do you know if there's a way to make vacancies on it?
Vacancy. What do you mean vacancies? Like a defect?
Like defects.
Yeah. You can tag an atom and remove it.
Oh, really? Yeah.
Yeah. Like so, for example, but right now because we're just reading, it's not a real atom, so you can't remove it. Yeah. But if you extend it, like if you do diagonal reading, and then you actually extend it, then yes, you can just like remove one.
Oh, nice. No, I was looking at basically a paper working with copper manganese arsenide where they were talking about how defects, and I was like, that'd be good.
Yeah, no, you can do a lot of stuff in this thing.
Okay. Okay, not now, but maybe later we will have to make a break. Let me just check my diary. What else? 12 o'clock. So we've been running 1 hour and a half now, yeah?
Yes.
Are you tired? Are you okay?
I'm okay, but
okay. I would like to finish the construction. So if we go CO, we have still 8 atoms of silicon and 2 atoms at the bottom hydrogens. So now, as I said, you would like to terminate your silicon atoms at the bottom with nice, good hydrogens, so there will be no strain in the system. So you need to run WASP with that smallest possible cell, with sufficient number of K points. Now you have to use KP surface option. So there will be no K points in the Z direction, but will be many K points in the X and Y direction. And you will have to freeze all atoms apart from hydrogens. So let's look how this can be done. This is really easy. So you can, yes.
They're already frozen, aren't they?
No, they're not frozen. So if you look
at
the, no, they're not. Look. Oh, this hydrogen. Oh, yeah. So all atoms are frozen, and atoms at the bottom are free to move. You see TTT. Yeah. So I believe when I implemented this, I made this. Yes. So it is done by default. That's good. That's good. So we don't need to do anything. But what I wanted to show you simply that the option FD, which is FA, frozen atoms, works in such. So it shows 1 to 8 frozen, by the way, here already. But it works in the same way as tagging.
Yeah.
When you tag, you can do that. Actually, there's another option, TT tagging. I don't know if you tried this. This is a more complex option. It allows you to tag in a more sophisticated ways. Yeah. So let's just leave this option. So, and FA, I think it works that way. FA works that way. So if you go FA, not set. Now all atoms are not set. So you see CO, all atoms are free to move.
Free.
Yes, we would like to have atoms from 1 till 8 to be frozen. What I can do, I can leave, I think this should work. Let's see, even though I displace more atoms than necessary, I believe I did implement that. Let me see. So normally I would remove this visualization option, and I would go with control like this. Yeah, so this way I only tagged my atoms, silicon atoms, and left hydrogens untagged. Then I will go to that screen, type FA. Now we have atomic numbers by atomic numbers, because this get selection option gives me atomic numbers. Then I click get selection. It gives me 1 till 8, enter, and exit with the current set, which is P. So now my atoms are properly frozen. So now we can see atoms of the silicon are all frozen, and the hydrogens are free to relax. Okay, so we've done this. So now, basically, now we can save this as our working cell and run WASP to relax hydrogens. WASP would relax hydrogens. So we have to save it, make it a postcard file, run WASP. WASP will create a concar file with the final geometry, and that would be your input file for the next setting session. So now we imagine this would be my file which I read in after WASP run.
Yep.
Okay, so now these hydrogens are properly kind of positioned. And we would like to construct an extension along the surface. So for this we can use this diagonal breeding box. Say for instance, I never remember in which direction but let's try 0, 1 in one direction and 0, 3 in another direction, and of course 0, 0 in the z direction. This way we constructed something like that. Now that was the wrong one, so I will explain you what I mean by that. So we have to do it other way around. So EX 0, 3, 0, 1, 0, 0. Hopefully that would be would be the right one.
So I'm confused.
No,
why is that the wrong one?
I think the first one was the right one. This is the wrong one. Yes. So let's go back. So all one goes first. Okay. Because I would like to construct 4x2 extension. Yes, I think this is the right one. Yes. So you see, this is my extended cell. It contains quite a few atoms. Yeah, we already have a lot of atoms, right? And by the way, you can see automatically all hydrogens are tagged as free to move. But when we run WASP, we would like these hydrogens to remain in their positions. So we need to make them frozen now. So in order to do this, what we can do, and we also would like to have bottom atoms of the slab frozen, yes? So before I do anything else, what I do, let me take the whole thing at the bottom, yes? Then I go to FA, This would nullify this set and FA again. N get selection. You see the selection is more complex now.
Yeah.
And leave. So now you can also have a look which atoms are frozen. So I removed this selection here, and then there is an option FD, display frozen atoms. FD, and it shows me this selection again. So we've done the right job. We have frozen the silicon, 2 layers of the silicon atom, or 1 layer. You can freeze more, and the hydrogens. So only the upper atoms will be free to move. Let's see what CO says. CO says that. So all hydrogen atoms are frozen. Silicon atoms, however, only frozen which have the lowest Z coordinate. The silicon atoms with this -2, -4, -5 are free to move. So we have 1, 2, 3, 4, 5, 6 layers free to move, and the bottom are all frozen. At that stage, you may want to save this cell just as a sum of your intermediate constructions. If you want, you can save it. Yeah, give it a name, whatever. But now we would like to construct the right termination of the surface. Of course, the positions of atoms are very symmetrical. So if you run WASP now and allow the system to relax, almost nothing will happen. These atoms would move mostly in the Z direction because of the symmetry. There will be no forces in that direction along the yellow line.
Okay.
Yeah, that is what you would like to have, because you would like to have these atoms to move towards each other. So in this way, they will establish. Look at on my face screen. They will establish bonding between themselves, and this way they will be not having just 2 bonds, but having 3 bonds. That would reduce the energy of the system. So what we need to do, I believe, now I'm a bit confused, but I think what we need to do, we need to take this atom, this one, and this one, and move towards each other, and do the same for these 2. Yes?
Okay.
Can you please explain again why are we doing that?
Say again?
Can you please explain again why are we doing that? I'm not quite.
Yeah. Because of the symmetry of the system. If you run WASP, you will find that components of the forces on these atoms in that direction will be 0. The symmetry of the symmetry, because this atom interacts with that one and that one in the same way.
Yeah.
So in order to allow WASP to relax the geometry in the way you want, you need to give it a little help. Yes. So if I move this atom towards these atoms towards each other, there will be non-zero force acting in that direction, and they would start moving. They will move, and then there will be a certain new geometry established.
Is that we are trying to break the symmetry so that the atom can
break the symmetry and construct the initial geometry as close as we possibly can to the final geometry we expect.
Okay. Yeah.
Because if we don't do this, WASP will not do this for us, or may relax to a completely different geometry.
Yeah.
If you remember our discussion of the potential energy surface a long time ago, there are many minima. We have to start from the right minima, from the right potential well, to be able to relax into the minimum of that well. Otherwise, it may go somewhere else. But in this case, it will not go anywhere, because the forces will still be 0. So, right. So now I will show you how to move atoms. So I have created a rather sophisticated system of how this can be done. What is that?
I don't know.
It's my side, so I mute myself.
No, this is like drilling sound.
Yes, it looks like.
Yeah, it's from my side, so I mute myself.
Okay.
Yeah. Are you sure that nobody is drilling into your room like a secret passage?
I hope not. It's my neighbor. I hope not.
So you look carefully. Maybe, yeah, you need a dog or a cat or a mouse
Yes.
for that thing. Right. So what is our goal? Our goal is to move these two atoms towards each other in the same fashion, to move these two atoms towards each other, and these two as well in the same way. So basically what we can do, we can take these four atoms, these four, and move them in that direction. We need to establish direction. Direction can be established either by Cartesian axis. So let's remove this toggle vectors option and put the axis Cartesian axis. So now we have, actually in this case, it's much easier because we can just simply say move along the y direction, yeah, along the green vector. But in other cases, you can move towards an atom. In that case, if you move this atom, you can move it towards that atom. So it will work out the direction automatically.
Okay.
Right. Let's try to understand what are these atoms. So for that, show numbers would be a useful option. So this atom is 25.
5.
57 is this one. 41. And this is 9. Okay.
Yes.
So we tag them.
So we're tagging 9, 41, 25, and 57.
So 9, 41, 25, 57. You can put either comma or a space. Okay, we have this atom tagged. Now we have to move these atoms. Move atom is the option MV, move atom. Direction, either 2 points or as a vector, or displacement in Cartesian coordinates. In this case, this probably is the best option. We displace in Cartesian coordinates along the y direction only in the negative direction, yes? So say minus 0.3 and 0. Now watch the screen. Oop, they moved. Did you see them moving?
Okay.
Yes.
So
no, you didn't. Let me. Oh no, I will move again. I will move again by a little bit. So again, displacement. 0 minus 0.20. So
okay, you put the entire vector.
Will be 0.5. Yes. Now look at the screen. These atoms will move now. Just give me a second.
This is in angstroms, right?
In angstroms. Everything is in angstroms.
Okay.
Now look. Yeah.
They move a little bit.
Yeah. So now we will take 4 other atoms. This one, this one, this one, and this one, and move in the opposite direction by the same amount.
Okay.
So we need to tag them. Okay. So let's see what are the options or what are the numbers. 8.
1, 3.
Let me remove the vectors because they bit. Okay, it's 17, 49, 17, 49.
1 and 3.
1 and
33.
33. Yep.
Yes.
1 and 33.
I have exactly the same ones. It's very good.
Yes. Yes. Now. Now tagging is off. By pressing tag, you nullify the previous, so you have to do it again.
Yes.
1, 33, 17, 49, right? And now go to move.
That's so cool.
We go to move. Yes, and this time for 0 plus 0.50.
Okay.
Okay. You see, they're still not moved enough. What I wanted to show you that if you move them enough, the software, this chimera, would find that the sum of the van der Waals radii of these are smaller than the distance and would run a cylinder between them, the bond.
I see. Okay.
Yeah. So let's not waste time on this. But if you do this, this is what you will find. So we actually have prepared now our surface for the relaxation for the 4x2 reconstruction. Yeah. Oh, it's 2 by 1 reconstruction we've done. I can't remember. 2 by 1. For 4 by 2, we have to make one atom slightly bigger. It would be slightly asymmetric. That's another thing. So we need to raise these two atoms and these two atoms slightly up.
And we can do the same thing, but move on the Z.
Yes. If we now look at this tutorial, I think it does this. So we have done this, you see, but probably it does say by how much we should have moved them.
Oh, no, it does. It does. 0.2.
But we have moved by 0.7. We have moved by 0.5 only each. Yeah, so it has to be by 0.7, I think. And this way, we would construct that, but still.
But it doesn't matter, does it? Like how much you do, as long as it's a little bit.
Of course, I'll just for visualization purposes.
Yeah, okay.
But then we have to make it, you see, make it asymmetric. So this is what you do with the surface. You bend one dumbbell in one direction and another in another direction. So what we have just constructed, I think this is called, it has a name, probably 2 by 1 surface, because these two cells, this one and this one, are equivalent.
Yes.
So 1 by 1 would be just this line. But we move these two together. So now these two lines together is 2 by 1. And this cell is equivalent to this. So we have 4 times repeated the same cell.
Yes.
This is what we have up to now. Yeah. So this is 4 times extended cell. So this is a 2 by 1 reconstruction. We can do 2 by 2 reconstruction if we put this atom up a little bit. What is suggested here in this tutorial by 0.2 angstroms up. And the other atom, I don't think I moved. And on the other dimer, you would put the other atom up. Yes, this would make them like this, and you repeat this here as well.
Yeah, so you just buckle them.
Yeah. Of course, we could have constructed that cell. Remember when we extended the primitive cell, surface primitive cell, we did it by 2 by 4. We could have done it 2 by 2. Then we would do this construction here, and then extended the result, and that part would appear automatically.
Okay, yeah.
Increase. So what we're going to do now is this. I will lift this atom, that atom, and that atom. You see?
Okay, so
chessboard. This, and this. So we tag them. First tagging 0. Now tag again. We want to. Which atoms are these?
I think it's
57. I think no.
Oh yeah, 57, 17, 41, and 1.
Yes, 41 and 1. And we move them up by 0.2. Oop, yeah. Now we tag again. Now we need the other ones. 25, 49, I think. It's very annoying, these numbers are so small. 49, 9, and 33. And we move them as well by 0.2. So now if we look at that, what we just done from a side. Oh no, undo.
Why?
You need to move it down, right?
We have to move them down, I think.
Yes. So now we need to do minus 0.4. Oh.
No, I did undo. So
Okay.
equal to 0, yes?
Yeah.
So
Yeah.
we tag them again. So let's do the tagging. So we can just copy and paste the previous tagging. This one.
And then I'm gonna do.
So let's see what will happen if I move them down.
Haha.
Right. So now we have this funny surface. So this is 2x2 reconstruction. And 4x2 reconstruction would be if these dipoles do not repeat themselves.
Yeah.
Okay,
And
so
the other side there.
So
the other way.
This one and this one become antiphase.
Yes.
Okay, so basically this is what you can do with tether. And at each point you can save. Yeah.
Oh yeah, let's save this. Good point.
Right. So I think when I have gone with you through a number of options related to surfaces. So we can save this. Of course, our construction is here. We can still see target atoms, but just for us to see. Yeah, we can attack them. And save, go to save option. There are many more options here. You can always save files at the right step, and so you would not lose what you have done, yeah, what you've been working on.
Yes.
All right.
That was pretty cool.
So do you think that is enough for now?
Yeah, I think that was pretty good.
So at that point, I think you should be able to try yourselves to create something. And
Okay.
Put a molecule on top. Let's put a molecule.
Oh,
There's
yes.
something we can still do.
Yeah, we have
Yeah.
space.
So suppose
Where's
that surface is the relaxed surface after we run WASP. So now we can run this surface, and WASP will relax atoms and would probably move these atoms closer to each other, even more. Yeah. But let's ignore this and let's just extend this surface a little bit. So we will extend it, say, I would say to have enough, we would need to extend along that direction, say, along that direction, we need to extend probably
in X
4 times. Yeah. And along that direction, maybe just twice, right? Of course, we don't remember which direction is which, so we would toggle axis.
Yes.
So this is the y direction. Look at the largest vectors. Along the y direction, we have the second largest vector. So along the second largest, so the second largest vectors need to be increased 2 times, but the first one increased 4 times. All right, so that's something. So along the direction a, the first of the first vector, we do 0, 3. That means 4 times.
And then 0, 1.
0, 1, and then 0, 0.
Yeah. But
oops, we have quite a big surface now. Oh yeah. Yes. It has 640 atoms.
Jesus.
It's probably too big. It's probably too big.
Okay.
Maybe let's do undo. And let's extend it, say 0, 2, and still 0, 1, 0, 0. I would say that's better.
Okay. But if we wanted to put like a C60, which is pretty big.
Oh yes. You will have to put C60, then breathe it and see. Actually, I may have C60.
Yeah, we do have C60 here.
Oh, let's put C60. Where is it?
Well, it's
I don't know. It's Concar C60.
Yeah, it's on the the.
Oh yes, Concar is fantastic. Well, let's have a look. What is this? Concar. Oh, what? Concar C60. Oh no, it's a small c.
Yes.
Oh, you see, in that file, the lattice vectors are very large, but
Yes.
this will be ignored. It will respect the lattice vectors we have right now. Okay. Fantastic.
How do you add this geometry
there's
here?
option add.
Where?
Add atoms from another file.
80. Okay. An atom, another file. Yeah. Oh no, I found it.
So now you have to see which format is this. This is old WASP format. If you see, there's no silicon.
Oh, there's no
so it must be option 3.
Yeah. Okay.
Then we say Concar C60 here.
C16.
And hopefully then just watch the screen.
We need to put the species. Carbon.
Species, it would be carbon.
Ta-da!
So you see, it embedded it into our structure because initially it was in the center. If one of the atoms would be exactly at the position of existing atom, Tether would complain. I can't remember what will happen. Maybe it will crash, nicely crash, but maybe not. But if you look now at CO, you see the carbon atoms are all tagged automatically. And that was done specifically for that purpose, that we would recognize that we'll have to move them up or somewhere. So I go immediately to move.
Okay.
Yeah. For, say, 005. Any better? Probably not. Move again. For 00, maybe 3. Oh, okay, maybe too much. But you see, so we can move it now somewhere in the center. So it's just easier for us to see the. Of course, nothing will change if you move it into the center. When you expand the whole thing, it will still be, there will be still big distances between the C60s. And you can see here by BB currently is off. So if we now run BB like this, see there's huge distances between them. So our cell is probably too big. You see, it's too big. We could have had our cell much smaller.
Okay.
So you see, it requires a bit of time to build this, but I think that simplifies that enormously.
Oh yes.
Because if you want to do it just on a paper, this is just impossible to do, almost impossible.
Yes.
Okay. If you move the C60 laterally, if you want it to be in the center of the cell, if you move it exactly above the same point as it was before, of course, it is equivalent geometry. But if you move it slightly off that point, it will be a different geometry. But WASP will correct you. When you run the relaxation, WASP will put C60 where it belongs. But again, it depends where you put C60, because there could be several minima for the C60 to be. And our surface is not just a simple kind of gold 111 when everything is very flat. It is not flat. So you may want to put the C60 at various positions above a dimer, slightly away from dimer, and relax, and each time check whether you got a new geometry or a different one, and calculate the total energy, the binding energy, and see what happens. Let's have a look whether our vertical vector is enough. Yeah. So what I do, I do a new BB. Yeah. It's probably not enough.
It kind of looks close, doesn't it?
But at the same time, this distance is probably too long.
Okay. So you can probably move the C60 down a little bit.
Probably move C60 down a little bit. So let's move it. It's still tagged.
Oh yeah, it is. Okay.
Say -2, I would say. Move down. Oh, okay, maybe that's okay. Still, the distance between the bottom atoms, these hydrogens of the next slab, and C60, that distance can be measured. But maybe it's easier here to go just to CO and just see. No, we can't, because this we don't have access to geometry to the coordinates of these atoms. So you can work this out. In fact,
can you just like check the numbers of the top atom of C60 and the bottom hydrogen?
Yes. So you have to check the atom number here, which will be here. So, just look at the largest Z component of carbon. The largest Z component of carbon is probably this 844. There's 851. Slightly different. 851. So probably 8.5. Then what you need to do is to look at the coordinates of the bottom hydrogens, which are here. They are minus 10, 15, and add to them the lattice vector we have in the Z direction, which is 25. So the hydrogens at minus 10, 15 plus 25, it becomes plus 15. Yeah. So this is plus 15 roughly. Yeah. Okay. Plus 15, and the upper carbon is 8.5. So we still have about 7 angstroms between them. Maybe it is not enough. Maybe at that point you would need to increase the third lattice vector a little bit more.
Okay.
But at least you have seen how this is done.
Oh, okay.
So,
Lev, how long does this take to run normally?
This one with WASP, that would it's difficult to say. I haven't run myself for some time now, and now computers are faster, so I don't know. But it used to be this kind of system would run a day, maybe.
Okay.
It depends on the computer.
Yeah, of course.
And don't forget, for this big cell, 0.00 K point sampling is sufficient.
0.00. Oh yeah, okay, yeah.
It's just gamma, so you can run gamma.
You can run
it's a big system.
Yes.
For any smaller cells, we constructed along the way, you would need K point sampling. Then you will have to use a non-gamma version of WASP.
Okay.
Okay, I think I don't know what else to tell you about. I think I kind of explained to you a lot of things in Tether. There's some other things. You can build a tip, say a FM tip. Maybe this is what we can look at next time.
Okay,
that would be great.
Yes, and then use the tip, put the tip above, and yeah. But that is easy. There's an option CL. Build up a cluster from the lattice. Yes, that's all. We can also look at constructing bulk system from scratch. Vibrations. We can look at the vibrations. That is a bit involved actually. Vibrations a bit. Maybe that's next. When you need it. So,
okay.
You can compare geometries. Move atoms wise symmetries, script for AFM modeling. Even that one I created at some point. Yeah, I don't know how useful that is, but it kind of works.
Okay. I'm gonna give myself a homework, and I don't know if Connor and Ying wants to do the same. I'm gonna do gold.
Yeah.
And
do gold bar, and then construct 1-1-1 surface.
Exactly. That's exactly what I'm gonna do.
Yeah.
And then I'm gonna try to. Yeah, I'm gonna do with gold and silver, and then I'm gonna try to put a C60 on silver, because that's exactly what we did on our experiments.
Yes. All right.
Okay. Oh, by the way, Lev, if I wanted to simulate water on C60, what I will have to do is first
simulate. Say it again. Simulate what?
Water at C60.
Water inside C60.
Yes.
Uh-huh.
So correct me if I'm wrong. So first of all, I create water, then I relax water, then I create C60, relax C60, then I put water inside the C60, relax everything.
Yes.
Then I create my surface, relax my surface. Then I put that water with C60 with water inside on top of my surface, and then relax that again.
Yeah.
Okay.
And then you have to understand what kind of lattice this C60 would create. Would it be just in the unit cell just one C60, or it's a more complicated lattice with two C60?
Yes, it is.
The unit cell, where C60 would like to go. So maybe that calculation should be done without water, because I don't think water would affect that in any way. How C60 stays on the surface, yes. On the other hand, gold is like very, very flat. So C60 would probably like to be anywhere. There wouldn't be any covalent bonding. It would probably be van der Waals interaction, which is flat interaction.
Cool. Okay.
Cool, guys. I have a 12 another meeting, and I need to relax. Maybe have a cup.
We'll let you go. It's been nice. Very, very. Thank you for showing us all this.
Yes. Thank you very much, Lev.
You're welcome.
I'll send you an email to remind you to send us the video and to send us the PDF.
Okay, so we can stop video now.
Okay.
And that would generate. That would